Welcome to another Molecular Knowledge Systems lecture on physical properties. This lecture focuses on physical property estimation using group contribution techniques. My name is Kevin Joback. In this lecture, I will talk about how, given a chemical's molecular structure, we can use group contribution techniques to estimate many physical properties. Properties such as boiling point, melting point, liquid density, liquid viscosity, and flash point. Specifically, I will focus on four main topics. First, I'll give a brief overview of why knowing about group contribution techniques is very important, and talk about the physical properties whose values can be estimated by group contribution techniques. Then, I will show a few examples of how accurate these techniques are, and show an example of using a group contribution technique to estimate a chemical's boiling point. We will then look a little deeper into why group contribution techniques actually work. We will look at how basic trends in physical property data actually suggest the applicability of group contribution techniques. And this will lead us to the last topic, in which I will briefly discuss the steps involved in developing a new group contribution technique. So why are group contribution techniques useful? Like all physical property estimation techniques, group contribution techniques are used to estimate the physical properties of chemicals. However, one of their key advantages is that group contribution techniques can estimate the physical properties of chemicals when the only information we have is the chemical's molecular structure. This is a very important advantage because many times we may be developing a product or process that uses a new chemical for which there are no measured physical properties. This is where using group contribution techniques is very helpful. Given only the chemical's molecular structure, we can estimate many of the physical properties we need for product and process design. We can estimate properties such as water solubility, viscosity, density. We can estimate heat capacities, boiling point, enthalpies of vaporization, formation and fusion, refractive index, and toxicities. Group contribution techniques are available for estimating the properties of pure chemicals and mixtures, organic and inorganic chemicals, polymers, and ionic liquids. Now, many group contribution techniques provide accurate estimates. For example, the Wilson-Jasperson method estimates the critical temperature with an average error of 2.4%. The graph shown here compares a set of estimated values against data values and shows that the technique produces very good results with very few outliers. Similarly, Joback's method for estimating the vapor phase heat capacity as a function of temperature gives an average error of 3.2%. And even group contribution techniques for the normal boiling point, a somewhat difficult property to estimate, give fairly good estimates. Even though the estimates produced by some group contribution techniques may have significant error, these estimates are often good enough for screening purposes. Screening for flammability limits, solubility limits, or toxicity limits. So how do group contribution techniques actually work? The key concept of a group contribution technique is that each part of a molecule contributes a certain amount to the molecule's physical property. We call these molecular parts groups, and we call these amounts group contributions. So each group contributes to the chemical's physical property. For example, consider Joback's method for estimating the normal boiling point of the chemical shown here. Joback's method states that each CH3 group contributes 23.58 K to the chemical's normal boiling point. Each CH2 group contributes 22.88 K. Each branched CH group contributes 21.74. Each ester group, the COO group, contributes 81.1, and each ether group contributes 22.42. So the first step in using a group contribution technique is to dissect the chemical's molecular structure into a series of groups, and then look up the associated contribution for each group. The next step is to combine these group contributions in some manner to produce a property estimate. Each technique has its own procedure for combining group contributions. Some techniques simply add the values together. Other techniques use complicated equations, accounting for all interaction between groups. Jovac's method uses a simple linear summation, so once we have the contributions for the groups contained in our new chemical, we simply add them together and insert them into this equation. For this example, we obtain an estimate of 420.8 K, which is in very good agreement with the literature value of 418.9 K. So again, to summarize, when we need to estimate the physical property of a new chemical, we first select a group contribution technique. Compilations of techniques are available in many chemical engineering references and software programs. Using the groups listed in our selected technique, we next dissect the chemical's molecular structure into groups. We retrieve the contribution of each group from the selected technique, and then finally we combine these values into an estimate using the selected technique's equation. For a simple model, group contribution techniques can produce very good results. So this leads to the question of why group contribution techniques work. To answer this question, we need to look at the relationship between molecular structure and physical properties. Here we examine data for the boiling point of normal alkanes. In this table, we list a series of normal alkanes and their associated boiling points. To the right of the table, we show the molecular structure of each alkane. For example, propane's boiling point is 231.1 K, and its molecular structure is CH3, CH2, CH3. Similarly for butane, pentane, hexane, heptane, and all the other alkanes up to dodecane. Looking at these structures, we see they all form the common pattern, CH3 on one end, one or more CH2 groups in the middle, and another CH3 group at the other end. This is shown by the formula here, where the value x corresponds to the number of CH2 groups. For example, octane's molecular structure is a CH2 group connected to 6 CH2 groups connected to a final CH3 group. To examine the relationship between x, the number of CH2 groups, and the boiling point, we can plot the number of CH2 groups on the x-axis and the boiling point on the y-axis. The points for the normal alkanes, propane, butane, pentane, through dodecane, form a smooth curve. If we regress a line to these points, we see that the deviation between the regressed line and the actual data is fairly small. The slope of this regressed line equals the amount the boiling point changes as we change the number of CH2 groups in a molecular structure. This value is a group contribution, specifically the contribution of the CH2 group for the normal boiling point. We can do the same analysis for another class of chemicals. Here is boiling point data for a series of perfluoroalkanes. The data are for perfluoropropane, perfluorobutane, perfluoropentane, perfluorohexane, and so on through perfluorooctane. All of these structures have the same form, a CH3 group attached to one or more CF2 groups, which are then attached to a final CF3 group. Again, graphing the normal boiling point versus the number of central groups, in this case central CF2 groups, we also find a fairly linear relationship. Calculating the slope of this regression line gives us a value of 28.1 K. This is the group contribution value for the CF2 group for the normal boiling point. And finally, here in our last example, we look at the boiling point of cycloalkanes. Here the X value denotes the number of CH2 groups in the ring. Cyclopropane has 3 CH2 groups, thus it has a value of X equal to 3. And cyclododecane has 10 CH2 groups, and thus has a value of X equals to 10. Again, if we take the slope of the regression line, we obtain a value of 33.2 K, which is the group contribution value for the CH2 group in a ring. Note that this value is different than the group contribution value for the CH2 group in a non-cyclic compound. These three examples showed how physical property values are related to molecular structure. In these cases, the relationship is linear. We can use these observations to hypothesize a linear model in which the boiling point is equal to the sum of group contributions. In this model, n is the number of times a particular group occurs in a molecular structure. For example, NCH3 is the number of times a CH3 group occurs in a molecular structure. And delta is that particular group's contribution. For example, delta CH3 is the group contribution value for the CH3 group. To solve for these group contribution values, we first collect data on many chemicals. In this example, data on boiling points and group occurrences. Group occurrences are the values for the n's in the equation. And then solve for the group contribution values, the delta values, using multiple linear regression. Multiple linear regression has become a widely used technique in the field of machine learning. The reasons are because there are many numerical methods that can quickly and robustly solve the regression problem. It is typically very easy to interpret the results of a regression. It is easy to vary or change variables. And regression results often provide guidance for the need to gather additional data. And, very importantly today, we can automate the regression process so we can quickly modify our problem and search for improved results. So in essence, there are 4 steps to developing a group contribution technique. In the first step, we need to compile good physical property data. By good, we mean several things. Obviously, we would like to have accurate data, but we also need data that provides sufficient variation in both physical property values and molecular structure diversity. In step 2, we need to select an appropriate set of groups. The main factor that must be considered is the molecular size of the groups we select. Groups with only a few atoms are broadly applicable, but they may not capture the underlying chemical behavior that is causing variation in physical property values. Very large groups are more likely to explain the variation in physical property values, but their larger molecular size reduces the number of molecules they are likely to occur in. The other factor we have to consider is that as we increase the number of groups, we have to ensure we have enough data to determine a statistically significant group contribution value. Unfortunately, this is often a significant limitation. Once we have compiled our chemicals and our data and selected our groups, we begin the process of dissecting structures into group occurrences. It is often at this stage that we realize we may need to modify the groups we were using, or we need to go and collect additional data. With our compiled data and group occurrences, we can now perform our multiple linear regression. The physical property data values are our dependent variables, and the group occurrences are our independent variables. These are inserted into our regression, and we then solve for our group contributions. To demonstrate these 4 steps, we will go through a simple example. In step 1, we compile good physical property data, boiling point data in this example. This compilation typically involves determining the range of chemicals to be estimated. Do we want to estimate only low molecular weight compounds or only higher molecular weight compounds? Are we considering many functional groups such as acids, alcohols, esters, or just a few functional groups such as hydrocarbons? And finally, we need to check that our data are accurate and that our data are actually data, not estimates. Unfortunately, many physical property compilations today contain a considerable amount of estimated values. In step 2, we select an appropriate set of groups. As we said before, it is desirable to have small groups so the technique will be broadly applicable. However, it is sometimes necessary to have large groups, large enough to capture the variations we see in physical property values. And finally, the groups we select should be clearly defined and understandable so other people can easily use and implement the technique. This last point is very important from the perspective of machine learning, in which the computer expects to have an unambiguous specification of the substructure to be used for molecular structure dissection. Now that we have compiled our chemicals and selected a set of groups, we begin the process of dissecting each chemical's molecular structure into group occurrences. For example, using our selected groups, the molecular structure of 1-methoxy-2-propanol is dissected into one OH group, one branched CH group, a CH2 group, an ether group, and two CH3 groups. Similarly, all other chemicals are also dissected into their group occurrences. Speaking of someone who many years ago did these dissections by hand using pen and paper, it is very productive to use modern computer software programs to perform these dissections. Now that we have compiled our boiling point data, which are our dependent variables, and our group occurrences, which are our independent variables, we can perform our multiple linear regression, solving for our group contribution values. There are numerous algorithms available for solving regression problems. Some of these algorithms are better than others at addressing some of the issues that arise in group contribution technique development. Issues such as the sparsity of our group occurrences matrix and issues of collinearity between group occurrences. In addition to the regressed group contribution values, multiple linear regression also produces a variety of very useful statistics. Statistics that can be used to guide the further improvement of our group contribution technique. For example, the R-squared value gives an overall measure of the goodness of fit, how well our regression equation captures the variation in our physical property values. A confidence interval is also typically calculated for each group contribution value. Examining these confidence intervals, we see that for some groups, the intervals are very small. This is a very good result and encourages us to believe that these group contribution values should be applicable to other chemicals not included in our training set of data. The intervals for other group contributions are seen here to be quite large. This could be because there are few chemicals in our data set containing these groups, or perhaps these groups are not appropriate for capturing the variation in physical property values, and we will need to choose different groups. In addition to these statistics, it is very important to test our group contribution technique to see how well it estimates physical properties. Here are the groups and contributions we developed from our example data set. As before, given a chemical's molecular structure, here we have 1-methoxy-2-propyl acetate, we first dissect the molecular structure into groups. We have 3 CH3 groups, 1 CH2 group, 1 branched CH group, an ether group, and an ester group. We then insert these group occurrences and group contributions into the technique's model and get an estimate of 413.8 K, which is in very good agreement with the literature value. Using this new group contribution technique on 518 chemicals, we see that it produces fairly good results, giving an average absolute percent error of 4.6%. As always, we should analyze our resulting group contribution technique to see if we can improve its accuracy or expand its generality. We should investigate if the model we selected was adequate. We selected a linear technique. Would a transformation of the estimated property give us better results? Can we remove the trend we see in the residuals? Should we modify the groups we selected? As we stated, we typically start with smaller, more general groups, and then if needed, try bigger, more specific groups. We can often consider second-order groups. These are groups that contain information about atomic neighbors. And should we modify our data values? This may sound like a strange question, but perhaps we need to make our group contribution technique more specific. Maybe we should exclude certain types of chemicals, chemicals containing certain functional groups, chemicals of high molecular weight or low molecular weight. Fortunately, today with the appropriate software, investigating these questions can be done fairly easily. So in this lecture, I hope you saw how group contribution techniques can be a very useful tool for estimating physical properties, how group contribution techniques arise from fundamental linear trends in physical property data, and how we can use regression techniques to develop new group contribution techniques. Please visit our website, www.molecularknowledge.com, for more information on physical property estimation and for demonstration versions of our Cranium and Synapse software packages. Both software packages use group contribution techniques extensively and can be used for property estimation, chemical product design, and developing new group contribution techniques. And, as always, if you have questions about group contribution techniques or physical properties in general, please contact me at my email given here. Thank you very much.